Okay, our lesson for today is on the binomial theorem. We're going to quickly go over what a binomial is, and then we'll talk about what the binomial theorem is useful for. So let's start off with what a binomial is. So a binomial is a polynomial with two terms, and the binomial theorem is a quick method of raising a binomial to a power. So say you had x plus y, that's a binomial in parentheses, raised to some n power. Now it's fairly easy if you're trying to find x plus y squared, but once you get to x plus y to the third or anything higher than that, it's going to take much longer. You're going to have to write out every single parentheses. So let's see if we can find some sort of pattern when we raise x plus y to some n power. So x plus y to the 0 power, well, anything to the 0 power is equal to 1. If we raise x plus y to the first power, well, that's just equal to x plus y. Now, x plus y squared, if we were to multiply this out, this would be x plus y times x plus y, so this would be x squared plus 2xy plus y squared. And then if you were to take this and multiply it by another x plus y, that would be x plus y cubed, and that would come out to be x cubed plus 3x squared y plus 3xy squared plus y cubed. We're going to do this for two more, and then we'll take a look and see what kind of patterns we see. So x plus y to the fourth, you take x plus y cubed, multiply that by x plus y, we end up with x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. And then raised to the fifth power, we have x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the fourth plus y to the fifth. Now, there are a couple of things that you should be able to see in terms of a pattern. You definitely see it gets longer, but longer by how much? Well, let's see how many terms there are. The first one has one term. When n equals 1, we have two terms. When n equals 2, we have three terms. When n is 3, we have four terms, and so on. So it looks like whatever n is, we're always going to have one more than that in terms of how many terms there are. So that's one thing you might notice. Another thing you can notice is that if you look at x and y and the powers that are on them, you'll notice this probably mostly when you have more and more terms. So if you look at the bottom row, look at the powers of x. It starts with x to the fifth, then x to the fourth, x cubed, x squared, x, and then no x, right? Or x to the 0. And then for y, same thing, but it goes the other way, right? Y to the 0, so it's not there. Y to the first, y squared, y cubed, y fourth, y to the fifth, right? So this pattern you'll see shows up constantly. So if you look at the second to last row, we have x to the fourth, x cubed, x squared, x to the 0, and y goes the other way, y to the 0, y to the first, y squared, y to the third, y to the fourth, and so on. Okay, so that's another thing to notice. Now look at the powers that are in each term. So say you looked at x plus y cubed. X cubed, that's degree 3, right? 3x squared y. So x squared, when y to the first, those degrees also add up to 3. X to the first, y squared, degrees add up to 3. Y cubed, degree is 3. Right, so notice that for each term within each expression, always has the same degree if you add up x and y powers. Okay, another thing you might notice is look at the coefficients. So you might notice that the coefficients, they all start with 1 as the first coefficient. And then the next coefficient looks like it's going to be whatever n is, right? So if you look at x plus y squared, the second term has a coefficient of 2. X plus y cubed, the second coefficient has a coefficient of 3. X plus y to the fourth, second term has a coefficient of 4, and so on. Okay? Another thing you might notice with the coefficients is they go up and then go back down, right? So we have on the last row 1, 5, 10, 10, 5, 1. And the second to last one, 1, 4, 6, 4, 1, right? It goes up and then back down. So another thing you might notice is there's a symmetry with respect to it. It's not just that it's going up and back down, but that once it goes up to the highest coefficient, it goes back down with the same numbers, right? It's 1, 4, 6, 4, 1, right? Same coefficients on either side, right? 1, 5, 10, 10, 5, 1. Okay, so there's a symmetry there too. So let's write those observations down. So we said there are always n plus 1 terms. We said that there's a symmetry with respect to the x powers and the y powers. So the powers of x begin at n and decrease by 1 each time, where the powers of y begin at 0 and increase by 1. Okay, and then we talked about the powers of each term. The sum of those powers are always the same. So the sum of the powers in each term, or the degree of each term, is always n. So if we were doing x plus y to the third, if you add the degrees of x and y within each term, it always equaled 3. And lastly, we talked about the coefficients, how they increase and then they decrease, but they also do so in a symmetric pattern. So I guess really the one thing we really need to figure out is, where do those numbers come from? Why is it 1, 5, 10, 10, 5, 1? So in order to find these binomial coefficients, we're going to use combinations. Okay, we're going to talk about what combinations are. For those of you who may remember from either Algebra 2 or maybe if you're in stats right now, you may have already learned combinations before. So a combination is generally notated as a capital letter C, and then on either side of it we use lowercase letters n and r. So the way that we would read this notation is n choose r is typically how we would read it. So what it represents is the number of ways to choose r items out of a group of n objects in any order. In other words, order doesn't matter. So how many ways are there to choose r items out of a group of n objects? So r is always going to be either equal to or smaller than n. You can't choose more items than there are objects in the group. All right, so how do you actually find this? Here's the formula for it. So n choose r is equal to n factorial all over n minus r factorial times r factorial. There's also a notation that looks like this. It's really like a set of parentheses, and then at the top you'd write whatever n is, and on the bottom you write r. So let's go ahead and take a look at an example. So here we're just going to apply the formula just so we get used to it if we're not already used to it. So find 8 choose 2. We're just going to apply it right into the formula. So 8 factorial over 8 minus 2 factorial, 2 factorial. Now a couple of things. So factorial, for those of you who maybe don't remember, factorial means you multiply every integer value going down until you get to 1. So for example, 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so let's simplify what we have here. The 8 minus 2 in parentheses becomes 6 factorial. And if there's any way for you to simplify without needing to write 8 times 7 times 6 times 5 times 4 all the way down to 1, we're going to try to do that. So for example, here we can write the top as 8 times 7 times 6 factorial, because 6 factorial is going to be 6 all the way down to 1. Now, why do we do that? Well, because we have a 6 factorial in the denominator. So instead of having to write all of the numerator out, the 6 factorial will actually just cancel. So that leaves us with 8 times 7 on top and 2 times 1 on the bottom, which is just 56 divided by 2, which is equal to 28. So that's your answer. Now your calculators do have the function where you can actually calculate what 8 choose 2 is without needing to use factorials, but it's good for you to know and to see the pattern when it comes to actually using the formula and you're not just blindly plugging into the calculator. All right, let's take a look at example 2. So this is just a different notation, but it's just 10 choose 3. Okay, so on the top we have 10 factorial. On the bottom, 10 minus 3 factorial times 3 factorial. And then we'll go ahead and simplify that 10 minus 3 to 7. Okay, and then now in the numerator, we'll do something similar as in example 1. So we'll try not to have to write 10 times 9 all the way down to 1. So it looks like we can probably get away with going to 7. 10 times 9 times 8 times 7 factorial. And then the 7 factorials will cancel. That leaves us with 10 times 9 times 8 over 3 times 2. So that looks like it's going to be 720 divided by 6, which is equal to 120. All right, example 3. 7 choose 0. Okay, so r is equal to 0. All right, let's go ahead and plug everything in just like before. Now what we end up with here is 7 factorial over 7 minus 0, which is just going to be 7 factorial, times 0 factorial. Now be very careful here. I know we're used to saying, well, if 0 is in the denominator, then this is not going to have an answer. But it's 0 factorial, it's not just 0 by itself. 0 factorial, in terms of how it's defined, is equal to 1. Okay, 0 factorial is equal to 1, 1 factorial is equal to 1. I know that's a little bit strange, but that's how we define factorials. Okay, so this ends up being 7 factorial over 7 factorial. Anything divided by itself is going to be equal to 1. Okay, let's take a look at example 4. 8 choose 8. Okay, so 8 choose 8. Here again, we're going to end up with an 8 minus 8, which is 0 factorial. And remember, 0 factorial is going to equal 1, which leaves us with 8 factorial over 8 factorial, which is equal to 1. So you'll notice that when you have r equal to 0, right, in the last example, or r equal to whatever n is, like in this example, you always end up with 0 factorial in the denominator. And when that happens, you actually end up with what? You end up with the same number divided by itself, which gives you 1. So notice how both examples 3 and 4 gave you an answer of 1. That's not a coincidence. Okay, let's see if we can find a pattern here. So notice the pattern. 8 choose 2 is equal to what? Well, it would be 8 times 7 all the way down to 1, 8 factorial, and then what cancels out? The 6 factorial cancels out with the 6 factorial. Now you'll notice that one way of going about thinking about this instead of having to write that out is if you see that pattern. So you always start with, well, in the numerator, it is 2 factors starting with 8. Why 2? Because r is 2. In the denominator, that's just going to be what? 2 factorial. Over here, we have 3 factors because r is 3, and we start with 10 because n is 10. All right, so 10 times 9 times 8, and then in the bottom, we have 3 factorial, just like how in the first one we have 2 factorial. So you'll notice that's always going to be the pattern. So if that's helpful to you, instead of having to write it out and see what cancels out, that's always the pattern that's going to happen. Okay, so it's r number of factors starting with n, and on the bottom, r factorial. Okay, another cool property that ends up happening when you are working with combinations is, take a look at this. 7 choose 3 is equal to 35. 7 choose 4 is also equal to 35. Again, not coincidence. Let me give you another example. 12 choose 1 is equal to 12, and 12 choose 11 is also equal to 12. So you'll notice here, if you look at the values of R, when the R values add up to, so if you look at 7 choose 3 versus 7 choose 4, the two R values we're working with add up to N, in this case that's 7, then those two combinations are going to be equal to each other. So same with the 12 choose 1 and 12 choose 11, those are equal to each other. So you could also say right away, well, 12 choose 2 is going to be the same as 12 choose 10. Okay, so a way for us to write that down, in general, we know that N choose R is the same as N choose N minus R. Okay, so how does this relate back to the binomial theorem? Weren't we talking about how we find x plus y to the nth power? What does all this combination stuff have to do with anything? Well, the combinations, if you remember how we got here, is that these are going to be helpful in determining what the coefficients of your expression is going to be. Okay, so we said that in the expansion of x plus y to the nth power, we know that there are going to be n plus 1 terms. We already wrote that down earlier. Now, depending on whether you have x plus y to the nth power, or if you have x minus y to the nth power, that will tell you whether the terms are going to be negative or positive. Now, if you have x plus y to the n, all terms are going to be positive. So you don't have to worry about that. However, if you have x minus y to the nth power, then it's going to alternate. So the first term is going to be positive, second term is negative, third term positive, and so on until you get to the end. Okay, so if it's x plus y to the n, all the terms are positive. If it's x minus y to the n, then all the terms are going to alternate, starting with the first term being positive. Okay, so if we were to expand some binomial x plus y to the nth power, we are going to remember that each term is going to have 3 components. The first component is the coefficient. Now the coefficient is going to follow this pattern: n choose 0, n choose 1, n choose 2, all the way up until you get to n choose n. So this pattern, which we can pretty easily calculate now because we talked about combinations, is also a pattern that's found in what's called Pascal's triangle, and we'll talk about that in just a second if you find that more helpful. But know that you can find the coefficient by using combinations. So that's the first component. Second component is the first term of the binomial x is going to have an exponent starting at n, and it will continue to decrease by 1 until it becomes 0 in the last term. And the third component is the second term of the binomial, the y term, which is going to be just the opposite. It's going to start at 0, so y to the 0, and increase by 1 until you get to y to the n in the last term. Now I know I'm using x and y, but it's not always going to be x and y. It could be an actual number. It could be, say, x plus 3 to the 4th power. Your y would be 3. Okay? Now let's talk about Pascal's triangle, because I think Pascal's triangle might actually be helpful for some of you instead of having to find n choose 0, n choose 1 every single term individually. So here's Pascal's triangle. You start off in what we call the 0 row, and we write a 1 there. In the second row, which we're calling row 1, because we're starting with row 0 as the first row, row 1, You write 2 1s there. Okay, so now what you're going to do is once you have that, the first term is always going to be 1, right? We saw that in our pattern as we kind of observed, looking at x plus y to the nth power going up to the 5th power. So the first term is always going to be 1. How do you get the next term? You get the next term by adding the 2 numbers above together. And then remember that the last term is going to be 1 as well, the coefficient. So here's row 2. We have 1, 2, and 1. So the 1 and the 1 add to 2. Okay, now remember we're going to gradually increase by 1 term each time. So the next row is going to have 4 terms. First term is going to have a coefficient of 1. Second term you do 1 plus 2, that gives you 3. Next term you do 2 plus 1, that gives you 3. And then the last term is 1. So 1, 3, 3, 1. Next row, start with 1, then do 1 plus 3, that's 4. 3 plus 3, that's 6. 3 plus 1, that's 4. And then end with 1. So 1, 4, 6, 4, 1. And you can continue this on, but really you just need to get to the row that your binomial is being raised to that power. So say you were trying to find x plus y to the 6th power. You want to know what the coefficients were. Well, if you have the Pascal's triangle written out for yourself, you can just go to that row. Now we don't have row 6 just yet, so we'll have to write a couple more. So we have 1, 5, 10, 10, 5, 1 for the next row. And then row 6 is going to be 1, 6, 15, 20, 15, 6, 1. And then row 7, same thing, 1, 7, 21, 35, 35, 21, 7, 1. Okay, so this is particularly helpful if, say, you're looking at row 6. You can probably more easily find those coefficients at row 6 doing it this way than individually saying, okay, 6 choose 0 is 1. 6 choose 1 is 6. 6 choose 2, calculate that, is 15. 6 choose 3, and so on. However, you do know that there's a symmetry about the coefficients, which is the result of that last general statement that we made about combinations where n choose r is going to be the same as n choose n minus r. If you were only asked, or if, say, you just needed to know what the third term in that expression is, then all you would need to do is find n choose whichever term it is and be able to find it that way. Using Pascal's triangle is a little bit overkill if you just need one term. But if you need to write out the entire thing, Pascal's triangle is very helpful. So let's do an example where we have to expand this binomial. So example 5, expand 2x minus 3 to the 4th power. Okay, so a couple of things before we get to actually writing down what this comes out to. So remember here, n equals 4, which means how many terms do we have? We should have one more than that, so n plus 1, which is 5, number of terms. Now we have 2x minus 3, so the minus in between means what? We're going to have alternating signs starting with a positive first term. So we'll remember that for later. Now let's write out our 5 terms. We'll start with the first term is going to be 4 choose 0 as the coefficient. Second term 4 choose 1, 4 choose 2, 4 choose 3, all the way till you get to 4 choose 4. Okay, that's the first part. Remember, we have 3 parts. So the coefficient we took care of. Now we're going to take care of the first term of the binomial, which in this case is 2x, right? Not just x, but 2x. So we start with 2x being raised to the 4th power, and then we go down. So 2x to the 4th, then 2x cubed, 2x squared, 2x to the 1st, 2x to the 0. Now we take the second term in the binomial, in this case 3. We'll worry about the negative later. Just take the 3, And now it's going to go the other way. We're going to start with 3 to the 0, and then go up as we go. So 3 to the first, 3 squared, 3 to the third, 3 to the fourth. All right, so now we're going to alternate the signs. So remember, the first term is positive, second term will be negative, and so on. So positive, then negative, then positive, then negative, then positive. Okay, now if you want to, instead of finding 4 choose 0, 4 choose 1, 4 choose 2, instead of calculating each of those, you can actually just use Pascal's triangle, which we just wrote down. And now you are looking at row 4. Right, so in row 4, we should have 5 terms. And if you look at the triangle, it looks like it's 1, 4, 6, 4, and 1. So those are going to be our coefficients for each of those terms. 1, 4, 6, 4, and 1. And now we'll go ahead and simplify each of these exponents as much as we can. So 2x to the fourth is the whole thing, so 16x to the fourth, 3 to the 0, and so on. So 2x cubed, that's going to be 8x cubed, 4x squared, 2x and 1. Working with the 3, now we have 1, 3, 9, 27, 81. And then transfer the pluses and minuses and simplify as much as we can. So we have 16x to the fourth minus 4 times 8 times 3, that's 96, x cubed. 6 times 4 times 9, that's 216, x squared. And then 4 times 2 times 27, that's 216. And then 1 times 1 times 81, 81. So that is 2x minus 3 to the fourth expanded. Now I know at first when you do these, it's going to seem like a lot of work because there are 3 parts to each term, and depending on what n is, you may have several terms you need to find. However, I promise you that once you get the hang of this, this is still much faster than trying to do out 2x minus 3, 2x minus 3, 2x minus 3, 2x minus 3, and having to distribute and then multiply it all out.